Hello and welcome to Vodcast 11.3. In this Vodcast, we will overview the concepts associated with Earth's seasons. Sadly, if you ask the average American what causes Earth's seasons, many of them would probably say that in the summer, we're closer to the sun, and in the winter, we're further away from the sun. Now that description works pretty well when describing what happens when you sit closer to a campfire versus further away from a campfire on a summer night, but put simply, that is not what causes Earth's seasons. In fact, in our summer in the northern hemisphere, we're actually furthest away from the sun, and during our winter months, we're closest to the sun. So that really defeats that whole line of thinking. To understand the causes of the seasons, we have to understand two important Earth motions, namely rotation and revolution. For rotation, I built a nice little model using a line. And if you take a look at my line, I have a white pushpin in the top and then a blue pushpin in the bottom. The white pushpin will represent the North Pole, and the blue pushpin will represent the South Pole. When we talk about the rotation of Earth, we're talking about Earth spinning about an internal axis. So imagine a line running straight through my line, down through the North Pole and out the South Pole. And if I spin the line about that axis like this, that's rotation. So I hope that you can see the smiley face here that I drew on the front of the line. And if I rotate the line one full time, and the smiley face comes back to you, we would define that as 1 day. Now here's where it gets kind of tricky, because with revolution, we're talking about the Earth going around the sun. So now I'm going to bring into play an apple. The apple is going to represent the sun, and I still have my line, which represents Earth. Now I'm going to talk about this in just a second, but Earth's North Pole does not point straight upward as it revolves around the sun. In fact, in our summer months, the North Pole will be tilted about 23.5 degrees towards the sun. And now, as I show you what revolution looks like, we're talking about Earth going around the sun, following a roughly circular pattern. Now this is really complicated, and I don't know if I'll be able to do it, but while Earth is revolving around the sun, it's also rotating. So if I spin it in my hands, I'm doing pretty good at this, there's rotation occurring. Okay, you get the point. There's rotation occurring while revolution is occurring. So hopefully that served as a nice little look at rotation and revolution, and I had fun doing it. I want to show you a real brief video that highlights the exact same concepts, just in case you weren't a fan of my little fruit demo. So hopefully the combination of my little fruit demo and that video helped you gain a good conceptual understanding of both rotation and revolution. Now let's shift our attention to what causes the seasons. The seasons are ultimately caused by our revolution around the sun. And the seasons are the result of changing sun angles and changing lengths of daylight. If you take a look at the image at the top of this slide, on the first day of summer for someone in the mid-latitude region, which is kind of close to our current location, the sun angle would be about 73.5 degrees, meaning that it is extremely high in the sky. Now, although the sun isn't exactly 90 degrees in this image, meaning that it would be perfectly straight overhead, I want to shift your attention to the picture below. And in image A, where it's extremely warm, somewhere in the tropics I'm guessing, sunlight is coming straight down at a 90-degree angle. And when the sunlight's coming in nearly vertically, there's a lot of energy concentrated in a given area. And those 6 yellow lines basically tell us that there's a lot of solar energy influencing this region. Okay, let's shift our attention back to the top image and look at part B. In this picture, we're looking at the spring equinox or the fall equinox. Either one would actually be applicable. The sun angle now is only 50 degrees with respect to the horizontal, meaning that the sun wouldn't be as high up in the sky as it was on the summer solstice. Now, what effect does that have on seasons? Well, let's shift our attention back to the lower image. And although this is demonstrating a 45-degree angle, which isn't exactly 50 degrees, it's close enough. Now, because the sunlight's coming in at an angle, the solar energy gets more spread out. That's why you only see 4 yellow lines on this picture. And then for our last consideration on this slide, let's take a look at the winter solstice, where the sun angle is only 26.5 degrees with respect to the horizontal. Because of that extremely shallow angle, this will be the shortest day of the year, And that incoming solar energy will be spread out even more so than it was in the previous picture. There's one other very important concept we have to consider in understanding Earth's seasons, and that's that our rotational axis is tilted 23.5 degrees with respect to the vertical as Earth revolves around the Sun. So let's start by looking at the summer in the northern hemisphere. The summer position in this image is right here, and we know that's the case because our rotational axis is tilted towards the Sun in the northern hemisphere. Now in the southern hemisphere, where the rotational axis is tilted away from the Sun, they would be experiencing winter, because the sunlight would be much more spread out in the southern hemisphere. One other note to make about the summer solstice is that the sunlight is hitting directly on the Tropic of Cancer, and as shown by this line, that is the latitude of 23.5 degrees north of the equator. Any region in the northern hemisphere that's reasonably close to this latitude will be getting sunlight hitting them almost directly head on. Now let's shift our attention to the fall equinox. Anytime we're in an equinox position, the sunlight is hitting the equator head on, and all locations on Earth's surface will have an equal amount of daylight. Now let's follow the revolution into what would be our winter solstice. For the winter solstice, our northern hemisphere is tipped away from the Sun at a 23.5 degree angle. The sunlight is hitting the Tropic of Capricorn head on, which is in the southern hemisphere. So all the sunlight that's coming into the northern hemisphere is coming in at a relatively shallow angle. At the winter solstice, we will have our shortest day of the year, and when you have a combination of diluted, spread out sunlight and then a very short day, you have a very nice recipe for the winter season. And then if we work our way back around to the spring equinox, we would once again see 12 hours of sunlight at all positions on Earth's surface, and the sun would be hitting the equator head on. So I know that we're being biased and focusing on the northern hemisphere, but that's the hemisphere in which we live. So keep in mind, on the summer solstice, we will have our longest day of the year, and on our winter solstice, we will have our shortest day of the year. At summer solstice, our rotational axis is tilted 23.5 degrees towards the Sun, and as Earth revolves around the Sun, it stays with that same tilt. So when you go halfway around this image, at our winter solstice, we would now be tilted 23.5 degrees away from the Sun. So the concept I'm trying to stress here is that our axis is always pointed in the same direction during revolution. Okay, that concludes this video podcast. I hope it's helped you understand what causes Earth's seasons. And I think the summary shown on the screen is a nice little cheat sheet to help you reinforce that understanding.